Okay, today we're going to be looking at our first part of the mechanics course on constant acceleration. We'll start with travel graphs. Now, I would use a travel graph if I've got multiple stages of motion, different accelerations, bit by bit. So I've got a situation here in my first example where I've got a particle moving over a time of 50 seconds. I've got a displacement time graph, so I've got figures of 20 metres there, 32 at A and B, and 40 at D over these particular times. And I've got a few things to do. First things first, he wants me to describe each stage of the motion. Well, I'm going from this point here, I'm moving with constant velocity for 8 seconds until I reach A, which is 32 metres away. I'm then at rest, that's zero velocity from A to B for those 17 seconds there. From B to C, I've ended up coming back towards the origin for a total of 12 metres in 5 seconds, yet again at constant velocity. And then at 30 seconds to 50 seconds, I'm moving away from the origin again, still with constant velocity, until I'm 40 metres away from where I started off with. And so we're asked to sketch a velocity time graph. So think about what we've got here. We've got a velocity of the first 8 seconds that covers 32 metres. So what I'm going to do here is this. That's constant velocity. So for 8 seconds, times in seconds there, like this, velocity in metres per second, I'm going to have a velocity of 4 metres per second, sorry, there. And then it will instantaneously go to rest for these 8 seconds. It's always hard to show lines along the axis there. At this time, from 25 to 30 seconds, it travels 12 metres back in those 5 seconds. So 12 divided by 5 is 2.4, and it'll be minus 2.4 for those 5 seconds there, and that to 30. And then I'm sort of running out of space here, I might have to just extend that a little bit. Time in seconds. 30 to 50, it goes 20 metres further away in 20 seconds, so I've got a velocity of 1 metre per second. And it's assumed that, as I say, the change is instantaneous. And there we go, assumptions. What assumptions are we making? That at these points A, B, C and D, the changes are instantaneous, so it goes from the speed of velocity, 4 metres per second to rest there, and then starts going back towards the origin for that little bit, and then it starts moving away from the origin again instantaneously. So, total distance covered, right, and then the average speed. The total distance covered is, it moves 32 metres away from B to, then at rest, B to C moves 12 metres back, and then C to D moves another 20 away. So 64 metres is my total distance, and the average speed then is that divided by 50. 64 over 50 is 1.28 metres per second. That's my average speed. Total displacement and average velocity though, well, in all, I've ended up going, I'm 40 metres away from where I was, so it's 40 over the 50, which is 0.8 metres per second. Notice the difference between the distance covered, because I go forward, then backwards a bit, then forward again, and the displacement. I've ended up a total of 40 metres away from where I started. So that's my first example. We've got a velocity time graph for example 2, just a sketch of one there, and it wants the corresponding displacement time graph here. Now, this is constant acceleration. This is a straight line graph that starts up with a velocity, goes through 0, goes down there. It looks like I've got more the line below the t-axis than above it. That will have a slight effect here. Remember that for a displacement time graph, the gradient is the velocity, so it starts off with its biggest positive velocity, and then goes to 0 velocity at the top. So this point here is that point there, and then it will carry on travelling like that downwards, and then it looks like I've got a little bit beyond there. So at some stage or other, when that triangle has the same area about here, that's when its displacement is 0, and it looks like, because it's going a bit further on, I end up with a negative displacement. But it's a n-shaped quadratic curve. And there's no numbers on, so that's all I can do with that. Third example is this. It says I've got a velocity time graph over 30 seconds. I go from the origin to Q, 5 seconds, velocity 4 meters per second, then to R, still at 4 meters per second, then to S, which is, oh, you know what, I didn't make a note of that, I'll just scoot back. I'm nicking it from the sheets I've got here. For some reason I didn't put on. That was 8 meters per second there, and then T when it's at rest. And the question is simply, well, there was two parts to it, but it's the same basic idea. Find the average speed, and to do the average speed I need the total distance covered. Distance covered is the area of the graph, so I can split it into two trapezia and a triangle. So I've got Q to R then. I won't use S because I'll use S for the point there. I'll say the distance covered will equal a half 10 plus 5 times the height between times 4 plus this one, the parallel line to the y values this time, so a half 4 plus 8 times by 10, and then plus a half is a triangle, base 10, height 8, and add it all up, and that's my total distance there. So what have I got then? I've got 15 times 2, 30, that part there. I've got the average of 4 and 8, 6 times 10, 60, and then 4 times 10, 40, so 130 meters. And then so my average speed will equal that, 130 over 30, which is 4.3 recurring meters per second. There we go. So it's equivalent to having a line there for that time, and that's my rectangle. Nice and straightforward. Example 4. Oh, all sorts of chit-chats and tell me that a particle starts from rest, so u equals 0, accelerates from 0.9 meters per second squared for 12 seconds, then it's constant speed for 16 seconds, then decelerates to rest. Total distance covered is 389 meters. It wants a velocity time graph, it wants the maximum velocity, total time, and displacement time as well. So this is your typical vehicle moving between traffic lights. It will accelerate, constant velocity, decelerate. It's always going in the same direction. It's always going away from the origin, so the distance will always be increasing at every stage. So first 12 seconds then, so from 0 to 12, constant velocity 0.9 there, so 12 seconds to whatever that velocity is. We'll work it out in a moment. And then constant speed for a further 16 seconds, so the t is 28, and then decelerates to rest with whatever that value of t is, the total time. And that's what I've got to find at some stage or other. I know that the total distance underneath is 389. I know that the acceleration as a gradient is 0.9, and so I can use that to find the maximum velocity, because the acceleration is simply the change of velocity over time. So v over 12 is 0.9, so v is 0.9 times 12, which is 10.8 meters per second. Nice and straightforward. Total time, well, you can split it into bits and bats. It's a trapezium. Students, for some reason, do not like doing trapezium rule, but it's there. I've got two parallel sides, so I know that 389, the total distance, is the average of the parallel sides. So it's t plus that length, which is 16, times the 10.8. So I can say that t out of 16 is a half of 10.8, 5.4, 389 divided by 5.4 equals, I need a calculator for once, 389 divided by 5.4 equals 72ish, and then minus the 16 there to get approximately 56. So t 56 seconds is my answer with that one there. Last thing it wanted was a displacement time. I know what the last figure is going to be. It's going to be 389. So what does it do then? Remember, our velocity is the gradient of this curve. So because it's a changing velocity, it's a changing curve here initially. So what it will do, it will start from 0, so the gradient will be 0, and then it will increase. So for the first 12 seconds, it's increasing, 12. And then we've got a period of 16 seconds where it's a straight line, 28, and then it will decrease to rest at that 56 seconds. And I know that that's 389 is my total displacement covered in the 56 seconds there. So it was a curve there, a straight line, and then a curve going downwards. So we end up with a 0 gradient, 0 velocity. Okay, I've got one more example to look at. I'll rub this off and put the details on. We've got a velocity time graph first. So the fifth one, we'll start like this. It's a past paper question. It says, the diagram shows a velocity time graph for a train as it moves along a straight horizontal track for 50 seconds. So it's doing all sorts in this case here. So I've got the velocity there. It starts off 18 seconds to a velocity of 5. It will then go through at 28 and bottom out at 38 there, and then down to -5, and then up to 50 seconds there, and that's my time. We've got various questions here. It wants the distance moved in the first 28 seconds. So it wants the total area under that thing there. So the distance moved will equal half times 28 times 5, 14 times 5, 70 metres. From that point to that point. The total distance moved by the train during the 50 seconds. So I can do the same sort of thing on the other side here. So it does that for 28 seconds. For B, the total distance will equal what it moved in the first bit, 70, plus half times 22 now. Times 5, 11 times 5, 55. So 70 over 55 is 125 metres. Hence calculate the average speed of the train. So speed is total distance, 125, over the 50 seconds, which is 2.5 metres per second. Nice and straightforward so far. We've got loads more little questions. So that's 7 marks there so far. Not a great deal too for 7 marks, is there? D, find the displacement of the train from its initial position when it's been moving for 50 seconds. Well, what it's done, it's gone 70 metres out and 55 back. So its displacement is 70 minus the 55, so it's only 15 metres away from where it started. And then the average velocity then is 15 over 50, which is 0.3 metres per second, because it's the total displacement divided by the time. And F wants the acceleration in the first 18 seconds. Well, all that is just its velocity, 5, divided by the time, 18, changing velocity over changing time, 5 over 18 metres per second squared. Okay, so remember that for a velocity time graph, your acceleration is the gradient. For a displacement time graph, the gradient becomes the velocity. velocity time graph, your distance covered is the area of the graph. Be aware of distances above the axis, distances below the axis, because then you'll end up with the difference between distance, your scalar, and displacement, your vector. And hopefully, that's all there is to it.